Starting out, Sage, a lot of these you'll be able to kind of do in your head mathematically, but I'm not going to try and make them work out all evenly. Eventually, we're going to be in the wonderful land of you need a calculator. But for now. So 2 more words. We introduced the concept of a subscripted I for initial, beginning, starting, and a subscripted F for final, ending, last part. So xi would be initial position, xf would be the xi would be the initial position, xf would be the final position, di would be your initial distance, df would be your final distance, vi would be your initial speed or velocity, vf would be your final speed or velocity. Here we go. Let's answer some questions. A car leaves home, drives 10 kilometers west. What I tend to do, if they give me compass directions, I tend to, somewhere on the page, draw a little compass rose, like that. And you may, if you want to, make a little note, positive, positive, negative, negative. A car leaves home and drives 10 kilometers west to the store and then returns home. Now, I got a bit of a problem because I just realized my picture doesn't match the direction. So can you cross out the word west right here? You have to make it, I'm pretty sure that's east. Mr. Dueck was typing in a hurry. East. Question A asks, what's the car's initial position if it starts right here? We would say its initial position was 0 kilometers. That's its origin. That's its starting point. Hasn't traveled anywhere yet. Home is going to be our reference. What's its final position? Oh, you know what? Let's use the correct variable. We can use d equals or x equals. What's its position while at the store? Someone said it, you're right. Now, west or east, you could either write it this way, 10 kilometers, and then do a square bracket with the letter E. Or, what's another way to show east? Positive 10. Which one's right? Yes. No, really, Mr. Dueck, which one's right? Glance at your answers and see which one they want you to do. If it's multiple choice, glance at the answers and see which notation they want you to go with. By the way, I much prefer this. It's less writing, so, but this is obviously clearer. East. What distance did the car travel for the entire trip if it went there and back? Someone said it here. You're right. Who said it? Someone said, yeah. Yeah, said it. Speak up. 20. So, what's my symbol for distance? No arrow, right? That's a scalar. D for distance, vector bar, D for position or displacement. Oh, displacement. What's the displacement the car traveled for the entire trip? 0. 0. Okay. What if the picture had actually been correct and the car had traveled west? How would I show its position while at the store? Negative 10 kilometers, or 10 kilometers, square bracket, W, close square bracket. Time. 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 What would be a good symbol to use for time? We're going to use a lowercase t. Is a concept that describes, and I've got to check my notes to see what the heck I was wanting to get at here, Mr. Dueck. There it is. R. Give me a second. Yeah. Oh, there it is. Sheesh. That's really obvious. Time is a concept that describes when an event occurs. By the way, in terms of physics, time, very mysterious. We know what it is, sort of, but it doesn't work the way most of you think. Many of you think that time doesn't change. Einstein showed that time is different for everybody. As soon as you start to move, for you, time is slowing down. Now, if you're walking, Julia, time is slowing down like on the 80th decimal point, so it's not noticeable. But GPS satellites, which move very fast and have very accurate clocks, time slows down enough for them that they actually have to take it into account in their calculations when they're figuring out where you are on the Earth. If they didn't, they'd be off by about 200 meters for your position. And as you get closer and closer to the speed of light, time gets slower and slower and slower and slower. What that means, this is what Einstein showed. By the way, you're not writing this down. This is me going off on a nerd tangent. What this means, Julie, it turns out that if you're a photon of light, for you, time does not exist. Does anybody know how long does it take light to travel from the sun to hit the Earth? Yeah?
8 minutes.
8 minutes for us. How long does it take as far as the light is concerned? Instant, because no time passes for light. In other words, the light from stars that's several hundred million or several billion years away, for us, as far as the light is concerned, because time does not exist for it, traveled instantly. Time is weird. Very cool, but weird. Pick up your pencils again and we'll write this down now. This is not, that was a little Physics 12 rant. Initial time. What letter am I using for time? T. What was my abbreviation for initial? T, little subscripted I, is when the event starts. Final time. How could I write that? T for time, and what's a good abbreviation for final? TF is when the event ends. That may seem obvious, but let's at least write that once. What we're almost always, thank you, what we're almost always interested in is a time interval. Usually when you're measuring with a stopwatch, you start it, you stop it. It's a time interval. We have a symbol for that as well. What does that little triangle stand for? I kind of mentioned it last class. We're going to put it in our notes in more detail. Pardon me? It's a delta, but what does it mean? Max. Change in. You can make a little note here. Triangle equals. When you see that, you can read delta. That's nerdy. But if you want to impress me, if you just read it as change in time, is the blah, 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 blah. You know what? Rather than give you an English definition, I think a mathematical equation is worth 1,000 words. Allison, all delta t is this. Final minus initial. In fact, on the next line where it says time interval is calculated by, delta t equals tf minus ti. Is that on your purple sheet? Can someone look? In the bottom there section? Yes? Is delta t on there? I know I got a bunch of V stuff. Is delta t equals tf minus ti on there? No? Okay. Let's do a couple of examples. So, from a picture, what's the time interval from the skateboarder to travel from the tree to the sign? What would delta t be? I put the distances on the bottom, but the times are along the top. Keep it obvious. What's the final now? What's the final time when he gets to the sign? What's the final time when he gets to the sign? Time. Up here. 5 minus. What's the initial time that he starts out at? in your head without a calculator. I'm serious. 5 take away 0. 5 seconds. By the way, do I need to put a vector sign above time? Time's a scalar. Time's a scalar. Now, that may really seem really obvious. What we're really saying, Conlon, mathematically, is it took him 5 seconds to get there. Yes, I recognize that, but I want to start out with something that seems obvious so that when we get to stuff that's not so obvious, we're going to use the same mathematical approach. By the way, do you notice what I did, Courtney? I went final minus initial, like I wrote up there. That works for easy stuff. It'll work for yucky stuff. Next page. What's the time interval for the skateboarder to travel from the fire hydrant to the sign? Okay. It's going to be final minus initial. Sign is the final. What's the time at the sign? Minus 2 seconds, is that what it says? So what's the time interval in your head, Joseph? And again, I hope that's fairly clear and obvious, but I'm doing that on purpose. So when we get to the yuckier stuff, we'll use Rachel, the same method. If it's 17.9 seconds and 13.6 seconds, it's still going to be final minus initial. Use a calculator. I stuck this in. I actually combined 2 sets of lessons that I did last year, and so parts of this are going to repeat, but I don't mind because you guys are teenagers and you're kind of not paying attention sometimes. Displacement describes, I said this, the change in position. Oh, but what did I just tell you the symbol for change in was? Delta, triangle. The next line, I'd like you to put a little star next to, another little star next to, another little star next to. This is actually really handy. In fact, I make my Physics 11s and Physics 12s chant this as a class. Change in anything is always equal to. And then my kids in Physics 11 and Physics 12 would say, I would say to them, what's change in anything? And I'm going to tell you what the answer is. Because that way, if they ask you for change in velocity, you'll know what to do. Or if they ask you for change in position, you'll know what to do. Or if they ask you for change in time, you'll know what to do. Or if you take physics next year and they ask you for change in acceleration, you'll know what to do. Or change in voltage, you'll know what to do. Or change in momentum, you'll know what to do. Or change in, you'll know what to do. Change in anything is always equal to final minus initial. Ty, what's changed in anything? I want you to say back to me, final minus initial. Ty, what's changed in anything?
Final minus initial.
Alex, what's changed in anything?
Final minus initial.
Taylor, what's changed in anything? You're laughing, but the reason I do that is every year I see a question where it says, find the change in velocity, and kids leave it blank. But if I had said to them, can you go with the final velocity minus the initial velocity, they would all know what to do instantly. So I'm trying to put that extra step in there. Julie, what's changed in anything? Mm-hmm. Knock, knock. Change in anything? Final minus initial. So, what does that mean? You ready? Here's our first bit of reasoning. Sage, can you read to me this first line? I said displacement describes what? And what's change in anything? What's change in anything?
Oh, minus initial.
Final. Final. Minus initial. I know it's tough to say. So you ready? We're going to put it together. Displacement is the change in what? And what's change in anything? You know what? That must mean that the displacement must be equal to final minus initial. Is that one on the purple sheet? I need a purple sheet to look at. So, I'll pause the video for 1 second. So I've gone on my final minus initial rant. Hopefully I've convinced you why it's useful. Again, some terminology. The SI unit for displacement, the SI unit for time is seconds. The SI unit for displacement, meters. Meters. So, what's the frog's final displacement? Well, looking at the picture, where did he start? 0. Where did he end? 9. 9 minus 0. Now, I know you see that intuitively, but if I give you something yuckier, it's going to be the same procedure. What's the symbol for displacement? That's not displacement. What's that? Distance. How do I turn that into a displacement? Vector sign. 9. 9 what? Let's assume meters. Direction. I don't know. They didn't tell me that was east. Oh, but you know what? It's in the positive direction, so I'll put a plus sign there just to make it that clear. And then if that way was east, then I could add that later, Courtney. Or if that way was north for some, I could add that. Or forwards, I could add whatever they need me to. Speaking of signs, watch for signs. Using vector quantities, opposite directions are given opposite signs. So, some useful conventions. I think turn the page for you guys. Right, capital R. What's the opposite of right? Left. And I'm going to go positive, negative. Or east. What's the opposite of east? Positive, negative. In fact, usually forwards and backwards. Forwards positive, backwards negative. You don't have to. I picked this word carefully. I said, Alex, some useful conventions, not some useful rules. You can let left be negative. And in fact, in physics 11 and 12, there's sometimes where it's so much more convenient to let down be negative. We'll do that because the math is much nicer. But we'll just make a point that we're doing it and a little weird at that time. We also have up, down, or north, south, positive, negative. So, here is a complicated diagram. This person is changing direction. What I tried to do here, Matt, is show you where they are at which times. So it's called a motion diagram for those of you who are wondering. So here we go. What's the distance traveled between 0 and 5 seconds? Symbol for distance is a D. And then it wants the displacement. I'll draw a line down the middle of the page. Symbol for displacement is that. Between 0 and 5 seconds, what's the distance traveled? At time 0, where did we start? 5. Where did we finish? So distance traveled is? What about the displacement? Now remember, I said this. Displacement is final minus initial. Cam, repeat what you just said. What was my final position or location? Minus. What was my initial? Now, to show, did we move to the left or to the right? How can I show that?
Square bracket thing.
Even easier than that, how can I show to the right? Psst, look up. How can I show to the right? Huh. Okay. And again, Jess, you may say, yeah, Dueck, I could have done that in my head. Yeah, we're going to get to yuckier ones in a second, but I'm going to show you final minus initial still works. What's the distance traveled between 0 and 10 seconds? Okay. So we got D equals, and then what's the displacement? Now, you ready? Watch my pen. Here's where I started. Move, 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 turn around. Move, 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 move. Ah. What distance did I travel? First of all, I went to the right. How far to the right did I go? And then I went to the left. How far to the left did I go? Distance doesn't care about direction. I walked 25 meters. Distance. What about my displacement? Don't worry about keeping track of anything. Displacement is going to be final minus initial. Change in. What's my final position? What's my initial position? To the right or to the left? Positive 5. Now again, you're saying, yeah, Dueck, I see that. It's that line right there. But in case it was more complicated, we can still get, or if I didn't have the picture, if I just had the data, I can get there. I can get there. Let's keep going. What's the distance traveled between 0 and 15 seconds? Okay, so D. Oh, no vector sign, Mr. Dueck. And then what's the displacement? All right. Between 0 and 15 seconds. So my trip looks like this. Walk, 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 turn around, walk, walk, walk. Right? And don't be scared if you have a diagram, Allison, to muck it up with like a little pencil, draw a little arrow loopy like I just did here. Okay. How far from here to here? How far from here to here? Ah. 5, 10, 15, 30. Okay. So I think the distance is what plus what? I'm going to go the 15 because that happened first. I'll go in order. We walked 15, turned around, we walked 30. I can do that in my head. 45 meters. I'll erase this. Displacement. Displacement, Julia, is change in position. Folks, what's change in anything? Final position. In this case, position minus initial position. What's my final position at 15 seconds? 10 is wrong. What? Negative 10. Right? To the left. Sorry, I shouldn't have said right. Correct. To the left. Boy, I'm going to have to work on that. What's my final position? Negative 10. Correct. 10 left. Minus. What's my initial position? 0? At time 0, I wasn't at 0. I picked this diagram very carefully. 5. All right. Negative 10, take away 5. My displacement, I ended up negative 15 meters or 15 meters to the left of where I started from. Is that correct? 1, 2, 3, 15 meters to the left. So even for more complicated ones, Matt, my method, final minus initial, still bails me out. And again, some of you are saying, yeah, Dueck, I was doing it intuitively, and that's fine. But I can tell you, I can make it tougher still. This will bail you out every time. Hey, let's keep going. Between 0 and 20 seconds, I want the distance. I want the displacement. Hey, try this one on your own. Try this one on your own. I'll give you a hint for the distance. I think it's that. Right? I think. I think it's that. But let me see. It's going to be. I think I go 15 to the right, 30 to the left, and 10 more. Is that right, Tyra? I think 55. Ready? Count with me by fives. 5,
10, 15,
25, 30, 35, 40, 45, turn around, 50, 55. Right? Displacement, which actually, although it's more mathematical, I think it's easier to find. Because all I got to do is find my final position. What's my final position? At 20 seconds, where am I? Minus. What's my initial position? What's my displacement? Or, Matt, if you were giving directions, 5 left. Or 5 west. A couple more and we're done. What's the distance traveled between 10 and 20? Okay. Let me erase this. Now we're starting somewhere different. Oh, starting here. Between 10, looks like I go to 15, and then I go to 20. 5, 10, 15, 20, 25. I think it's 30. I think it's 20 plus 10. Is that okay? Tyra, we can do our same trick, right? 5, 10, 15, 20. Turn around. 25, 30. Stop. Displacement. Change in position. What's change in anything? 20 seconds. Tyra, my joy. What's my final position at 20 seconds? Yeah. Minus. What's my initial position at 10 seconds? Yep. Looks like my displacement is, I guess, negative 10. I'm 10 left from where I started from if I start my stopwatch at 10 seconds. 10 meters left. What's the distance traveled between 5 and 20? What's the displacement? Try this one on your own. Oops, put a display. There we go. Get rid of the vector. Try this one on your own. See if you can get these two as well. So between 5 and 20, distance, and then 5 and 20, displacement. Between 5, that's here, 10, 15, 20. Final. Initial. Is that right? Yeah. So let's do some summaries here. So I got 40 and I got negative 20, or 20 meters to the left. Let's summarize here. Distance, time, and velocity. Remember we said, recall, quantities can either be scalars or vectors. Scalars only have, does anybody remember the word that I used here? Began the letter M. It was a fancy word for size. Close. Mass is a scalar. And magnitude. magnitude, which is really a number with a size. Vector quantities, Andrea, have both a magnitude and a, began with the letter D, direction. Vectors have magnitude and direction. So just to give you kind of a summary of the ones we're going to be looking at in Physics Science 10, so you have a chart somewhere when you're trying to remember which ones are which. We have distance, symbol D, scalar. Compare that with displacement, also a symbol D, but how do I show that displacement is a vector? Little arrow thingy, yeah, vector symbol. Vector. Time. What variable did we use for time? T. Scalar or vector? Time is a scalar. And then here's the two ones. I mentioned these. We're going to be looking at these over the next couple of days. We have speed and we have velocity. I'm going to write them both, one above the other. Both of them have a symbol, lowercase v. One of these is a scalar, and one of these is a vector. Which one was a vector? Which one was a scalar? Velocity was a vector, and speed was a scalar. If I was a good teacher, Matt, I'd have some dumb easy way for you to remember that velocity is a vector and speed is a scalar. I got nothing. So you'll have to come up with something on your own. So Matt, which one of these will I put the vector bar above? Speed or velocity? Scalar. Vector. A little more. An object's speed and its velocity can be described in different ways. Okay? Let's suppose, don't write this down. Let's suppose that you were traveling 80 kilometers. And let's suppose that it took you 2 hours. How fast were you traveling? 40 kilometers per hour. That's an average speed. I'm willing to bet sometimes you were going faster than that. Sometimes you were going slower than that, because to drive for 2 hours and never have your speed vary is very, very difficult. So we have something called average speed, which is how we measure freeway speeds, for example. Then we have something called instantaneous speed. And if you want to, you can draw an arrow pointing to this and write a little note here. Speedometer. Your speedometer gives you your instantaneous speed right at that moment in time. What's the speed on the low heat highway here? 80 kilometers per hour. When I'm on the low heat, sometimes I'm going a bit faster than 80. Sometimes I'm going a bit slower than 80. When I'm coming to a stop at a red light, I'm going way slower than 80. My instantaneous speed is whatever my speedometer says. But you know what the average speed on low heat is? 80. couple of more words. We have something called uniform motion, and that's when you have a constant speed or velocity. Cruise control. That's what we call uniform motion. Your speed's unchanging, which is kind of boring, but we're going to start there. And then we'll say, okay, what if you're allowed to speed up and slow down? It's a lot funner. So, it turns out, by relating, what's that? Distance or displacement? Which one? Distance. You can write the word distance, or you can do that. And what's that? Time. We can determine speed. Which is the, what's that? Distance an object travels. It may end up actually being a change in, a delta, divided by the time interval, delta t. Here is an equation from your purple sheet. You want to find the speed of something, which as a symbol is a lowercase v with no vector because it's a scalar. It's equal to change in distance over change in time. And what's change in anything? Final minus initial. If you know your initial location, you know your final location, subtract, that's your distance. You know your initial time, often it will be 0. On a stopwatch it's 0. Your final time. Divide those, and that's how fast you're traveling. This is a formula on your formula sheet. Remembering that change in delta is final minus initial. I'm going to get a little bit fussy here. The average speed of an object is the total distance, total d, the object traveled, divided by the total t. That's the question that Cameron answered a few minutes ago when I said, oh, if you traveled 80 kilometers in 2 hours, what's your speed? You went 80 divided by 2. You went distance over time. And you probably didn't even think about it. You just did it. But for more complicated stuff, it still works. Instantaneous speed, speedometer speed. That's the speed of an object at a very specific, time and time, Mr. Dueck, at a very specific instant or point in time. For example, what reads instantaneous speed? What did I say? Speedometer. Now, if you're not speeding down or slowing up, if you're on cruise control, then your average speed will be exactly what it says on your speedometer. You know why, Courtney? Because you're not changing your speed at all. So if you go to cruise control, average speed and instantaneous speed are the same. I'm going to write that down. For an object traveling at a constant speed, what we call uniform motion, the average speed is equal to its instantaneous speed. That's a lot of mumbo-jumbo boring stuff. But summary, nearly done. Put everything together. Okay. Distance and displacement are similar, but not identical. Which one is a scalar, distance or displacement? Distance. That part you'll have to memorize. Distance is a scalar quantity. Displacement is a vector quantity. What do scalars have? The fancy word for size that begins with the letter M. Magnitude only. Where vectors have magnitude and direction. Remember, the displacement of an object is its change in position. What's a shorter way to write change in position? Where delta, which is change in, means what? What's change in anything? Hey, folks, what's change in anything? Final minus initial. I know it's last block, but and I know you got a long weekend. We got to focus. Speed and velocity are also, let's try that again, similar, but not identical. Which one is a scalar, speed or velocity? Scalar. Velocity is a vector. And again, you can put the word magnitude. And velocity has magnitude. And what do vectors have? Both magnitude and what? Direction. Velocity is the rate of change of displacement, and it's given by the equation. That's speed. Where that's changing and that's changing. Or velocity equals displacement over time. That's velocity. Yep. Give me 4 minutes. Oh, okay, quick look, Bunny, go ahead. What's your homework? Try to go back up. Right here? Okay. Could be an earthquake. Might not be me. Now, Julie, do you have to memorize that? Say no. Here's what you have to memorize. You do need to memorize whether it's a scalar or a vector. I've given you a dumb way for velocity and for speed. The other ones you have to memorize. Distance, scalar. Displacement, vector. Time, scalar. That you need to know. Secondly, you need to know what's change in anything. Alex, keep the headphone out of your ear before I lovingly wrap it around your neck. Thank you. Talking to him. You're in the line of fire. Sorry. What's change in anything? Folks, what's change in anything? The rest of that, what I've given you, is all contained right there. Right there. It's all contained right there. So you don't have to memorize that part of things. What you have to be able to do is apply it. So, what's your homework? I got 2 things for you. Nice yawn. First of all, number 1. So number 1 for each of these pictures says state the initial position, call it xi. The final position, xf. You can use di and df as well, but when I was making this up, I used x. The distance, d, and the displacement for the teacher, I've drawn an arrow, Courtney, to show which way they're moving. Okay, so number 1, 2, 3, 4, 5, 6, and then 7 says do it without the diagram. That's part 1. And then I got a little homework handout too. Up for a sec. So I used someone else's handout, and it was typed in Word for Mac. And when I pasted this in, that's 0 right there. That's 1. That's 2. You can see the 2 and the 3 are kind of getting moved over. It was a Mac PC thing, but you can count. The 0 is the correct one. The 0 is the correct one. So for all of these diagrams attached to the lesson 1 homework, then the second handout that I gave you is this one here. Let me give you some hints about it really quick. Alex, shush. Thank you. I'm about to get there, but I actually want to be able to talk without people interrupting me. Here we go. Second handout. You guys got lots of time, okay? Is 8.1 part 1. So define the following terms. Complete the table. So the symbol, the unit, scalar, or vector. You can use S, capital S for scalar, capital V for vector. I'll figure it out. State whether they're scalar or vectors there. Indicate whether the direction is negative or positive. I hope that goes pretty quick. Turn the page, or next page over. I think I shrunk it down. Okay? Then, see if you can fill in the appropriate boxes by going, what's the change in time? What's the change in distance? Or if I give you the change in, can you figure out what the final must be? Well, you think about that. 1 is a bit trickier. It's going backwards sometimes. Number 2 is also fair game. Then, turn the page over on the second piece of paper that I gave you. Look at the back. Turn the page over on the second piece of paper that I gave you. Look at the back. Thank you. Here's a cross-country skier. So here's another little motion diagram. They move toward the east for 1 minute, then to the west for up to time 2 minutes, and then back to the east for time 3 minutes. I've given you all the numbers that you need. See if you can write their positions as vectors. See if you can calculate their displacements, total distance, total displacement. And then I attach the answers if you get stuck. You got lots of time to get this done.